Would you mind coming just a little bit closer and possibly finding someone to sit next to? Because I want to give out some little leaflets, and you're going to need some teamwork to fill them in. Yeah. Teamwork. So first of all, thanks very much, everybody, for... One between two, yes, please. I know it's the end of the day of a long week, and thanks all for coming. And I'm aware also that this is a slightly different format to normal. It's not going to be 20 minutes. It's going to be a bit longer. And I'm going to be asking you questions and asking you to fill out these lovely leaflets. So could I just get a show of hands who is currently using formal verification? Who's heard that Symbiotic EDA has released open source formal verification tools? Do you know there's free educational license? So if you're in academic or you're a student, you want to use formal verification tools, then you should definitely check this out. And it's my job to show you how you can get started. And if I do my job well, then by the end of the little session that we're going to have here, you should have some experience in writing some formal properties and having a bit of formal verification experience. So what is formal verification? Probably most of you are used to writing test benches. So you've already designed your code, and you decide you want to test that it's working as expected. So you write a test bench that tracks through the pathway through your code that you're expecting, check the results are okay, and then if the results are good, cool, it's tested. Well, formal verification works in a slightly different way. Normally, when people think about writing tests, they write the test bench and then they check the output. I was speaking to a guy yesterday who does formal verification, and he said the way he sees it is, with formal verification, you specify the output, and then it writes the test bench for you. So it uses a solver to validate that your properties are not going to get broken. So instead of, and that can give some good advantages, because if you are writing a test bench for checking your own code, you're probably not thinking about all the crazy things that could go wrong. And one thing that the solver does, very annoyingly, is find all the crazy little bits that it could do to crash your code. So probably you don't try resetting your softcore 10 times in a row and then inserting something into a register and then flipping a bit. But if that's what it needs to do to break an assertion, then the solver will find out a way of doing it. So to illustrate this, I'm going to show you the pipeline for this machine learning accelerator that we've written in Symbiotic EDA. And this is a simplified version. I've got a lovely, lovely animation. So probably you're all fairly familiar with pipelines. And this is the thing about this pipeline is we have a single ported memory, which we had to use because of the type of FPGA we were using. So we have 3 different pipeline stages that use the memory, and when the memory is being used, it gets highlighted. We've got our parallel multiply additions for the neural network, and then at the end we have the write. So we want to avoid a memory hazard in this pipeline. We can't have more than one instruction stage reading or writing to the memory at one time. So the way that could happen is if we had, say, a load coefficient instruction followed by a load data instruction, we get a memory hazard. So we're going to get corruption there. The issue unit, we need to write a rule and say that if we have a load coefficient, we need to space it out from a load data with an OP. Okay, fairly simple, fairly straightforward. And we continue as usual, but somebody has started loading new coefficients right after a write, so we get another memory hazard there. So this pipeline, the simplified version's only got these 5 stages and only 4 instructions, but the real pipeline has got 10 stages and 40 instructions. And you can probably imagine that if we are able to load the instructions in any kind of order, we could have some kind of interruption. The rules of the issue unit get more and more complicated. It becomes harder and harder to write a test bench that guarantees that we'll never have a memory hazard. So we can use a formal property to make sure that this pipeline will never issue a set of instructions that results in a memory hazard. And at the end of this presentation, I'm going to ask you to write those properties. And if you can do it, then I've done a good job. So I mentioned this earlier, formal verification uses solvers, SMT solvers, SAT solvers. I'm still learning a lot about this stuff. It still feels fairly magical to me. You set some properties and you give that to the solver, and then it goes away and tells you whether your properties can be satisfied or whether they're unsatisfied. So as a quick example for this, before we get into HDL and Verilog, I want to show you an example from using Python, using a cool library called PySMT that lets you connect to a number of different solvers. And here we're making a little puzzle. So it's a bit like Sudoku or something like this. We're asking the solver to assign numerical values to each letter in hello, each letter in world, and then to make sure that when you add up all the letters, they come to 25, and also that the sum of the hello word should match the same sum as the world word. So let me demonstrate that. So it goes away and thinks, and we get a nice little dump of how it is expressing this. There's a big Boolean expression, and here you can see we've got the hello has got to equal the sum of the world, and hello's got to equal 25, and here's all the numbers that it's chosen. So if I change the sum to something that it can't reach, like 95, and I run it again, because we're only allowing the solver to pick numbers from 1 to 10. It comes back with a no solution found. And that's a critical point for the formal tools, is that the solvers only return with a yes, I can satisfy this, or no, it can't be satisfied. Maybe your job is complicated and it runs for a week and you decide to kill it, but it's never going to tell you, I don't know. It's just going to say yes or no. So this example, we're asking the solver to find a solution for something. So one way to think about that is to think that the solver is proving that something is doable. So in terms of digital design, we can use this special keyword called cover to prove that something is reachable, that some state is possible. So I've got a very serious demonstration here. I'm not sure if you guys have heard of the wolf, goat, cabbage puzzle. Probably have. Man's got a boat and has to take the wolf and the goat and the cabbage. Okay, I'm not going to go into it. I see the nodding heads. So this is an example from our Lord, Clifford. And he's got 4 registers, one for the man, one for the wolf, goat, and the cabbage. And then we have inputs to tell whether we're going to move the wolf, the goat, or the cabbage to the other side. And here's the critical part here. We're saying that we want to see the place where the wolf is on the same bank as the goat and the cabbage all at once. So we want to cover that possibility. And then the rest is a setup, how the things move. Oh, and here we go, we don't ever want to have the wolf on the same bank as the goat, and we don't ever want to leave the goat on the same bank as the cabbage. Serious stuff, this. So we have our system Verilog file here, which is just the same that I showed you. And the new thing that we have is the SPY file. So we're going to be using SPY, Symbiosis, which is the open source tool that we're using. And here we're using mode cover because we're asking the solver, is this thing that we're looking for possible? You're allowed 100 clock cycles to find it. And if we don't specify an engine, it's going to use the default solver, which is called Yikes. If you guys know about solvers, we've got a few different available for us, like Z3 or Bulector. So then I run this with the -F switch. So that means that it removes previous data that the solver has generated. And we have a bunch of setup up here. It's checking whether our cover is reached, and we can see that it's reached in step 8. We've got a pass here, and then the final thing is a pass. And then we've got a new directory here called wolf goat cabbage, so that's the thing that wouldn't be deleted if we didn't use the -F switch. And in there we've got a bunch of files. And one of those files is a VCD file. That shows us the trace that the solver found that satisfies the cover. So we've got a recurring clock, and then here are the signals coming in to tell us whether we need to move the wolf, the goat, or the cabbage. So we're starting moving the goat, and then we move the wolf, we bring the goat back, we take the cabbage, and then we bring the goat back across, and then here we've got the man, the cabbage, the goat, and the wolf all on one side. So the solver's gone ahead and done that. It doesn't know what we're wanting to do, but because we've said we've used this cover function, its job is to find that for us. So the way that I think about the solvers is that they're good at solving puzzles, and using these tools, it's our job to define the puzzle. So, into the world of verification. The first part of verifying your module is the bounded model check. So, the way that this works is that in your design, we see it as a digital circuit. We're talking about HDL here and FPGAs, that kind of thing. The solver has a way of moving from state to state in a valid way. And then we can say something like, here's a nice picture. So the solver knows how it can get from an initial starting state through valid states. And we, using a keyword called assert, say that you're never allowed to hit one of these red states. So given our initial starting state here, on the yellow circles, is it possible to hit a red illegal state? Oh shit, he asked a question. Anyone? Here? From these two initial starting states? You can't, because we can see, I mean, this is a very simple design. So in this case, we can't. So a bounded model check here would succeed. So one way to think about this is it starts off in our initial state, and it checks to see if the assertions are holding or not. If they are broken, then the solver wins. It becomes satisfied, because the solver is always trying to be satisfied. And we lose, because it has just found a way of breaking the assertion. If it's unsatisfied, then it moves on to the next step and repeats the same thing up to a certain number of steps. That's the depth. And by default, if you change nothing in the SBY file, the depth is 20. So BMC, bounded model check, and induction, which we're going to cover in a minute, test safety properties. So cover checks that something can happen. Assertion, BMC and induction test safety properties. They prove that something will never happen. So that's usually what we're after when we're doing formal verification. We want to check that something will never happen, but often we will also want to check that something can happen. So for an example, if I make an assumption and I say that the clock can never change from 0 to 1, probably all my assertions will pass because the design never got a clock. So you probably want to use cover to check that your design can actually do something. So we have these two basic operators. Assume, like I just mentioned, you can use to control things, so we can guide the solver to solve the puzzle that we want to solve. And assert tells the solver what the state is that is illegal, so it knows whether it's done its job or not. So one way of thinking about assert is that the more assertions we add, the bigger the space of illegal states is. And the more assumes that we add, we decrease the size of all the potential logic combinations. So we reduce the space that the solver is working in. So that can help make things run faster. And as I said before, if you're making a careless assumption, one careless assumption can void the proof. So if I assume that clock is 0, we never get a transition. The design can't progress. And typically, you will always use assumes for your inputs, and you will use assertions for your local state and for your outputs. So here we go. First real exercise, using Verilog here, a busy counter. We have a clock coming in. We have a start signal and an output busy signal. If the counter is not counting and we get a start signal, then we load max amount -1 into counter, and then it will count down back to 0. And while it's counting, busy goes high. So first exercise for you and your partner is write a property that proves the busy counter will never count for longer than max amount. So feel free to discuss that. I'm going to give you 15 seconds, starting now. 1, 2. Anyone want to volunteer an answer? Jeremy. Like this. And we also need to put that in an always block. Anyone got anything different? Yeah. Won't go below 0. Actually, because it's an unsigned counter, we don't need to check that, but good point. I can see you're on it, and I appreciate that. So let me just show you the... So we've changed from mode cover to mode BMC, bounded model check. The depth is by default 20. I'm just going to put this in here anyway to make it explicit. And that's all we need to see there. There we go. So because I've already run SPY, it's telling me maybe you don't want to lose this data, so I need to give it a -F flag. Okay, so we get our startup as before, using yikes, but we fail on step 0. BMC failed. It tells us which assertion failed on line 22. We've only got one, so we know it's this one. And one of the cool things about these type of tools is that when we get a failure, we always get the trace. So if you're used to debugging big designs, you might have a gigabyte of traces. And it takes a long time to load, and you're looking through stuff. But with the formal tools, you just get 20 clock cycles, and there's the problem. So it makes it very quick to proceed and progress with finding bugs. So let's take a look at this. Right. Anyone expecting that? Why did the counter start here? Because it can. So we found a bug. We didn't initialize the counter. Yeah, I hear that. It's a simple example, just to give a flavor of the tools. But now that I've set an initial value, we can see it gets all the way up to 20 and then passes. And if it passes, then we don't get our trace. So if you wanted to see that it was working, that's when you would use cover. Okay. Double shift register. So we have now an input clock, a clock enable. We've got input data and output data. We've got two identical shift registers that are 8 bits wide. And when the clock enable is high, we clock input data in, and we get the output data out here, A and B. And then we have a signal, O data, which is just an XOR of A data and B data. So if A data and B data are the same, O data is always going to be 0. And then down here, we have a property. Always assert that O data is 0, i.e. that always A data is the same as B data. Will this pass bounded model check? We've got a not at first. Any other answers? One thing that you're not seeing here is that the shift register has an initialization and it's being set here. So you can assume that the shift registers start off at 0. So that probably answers your question as well. Okay, let's find out. Okay, we got a pass. No problem, we're there. So, what next? BMC is only the first part of this, okay? We're only checking the first n clock cycles, and there could always be a problem on the next one. Maybe we increase it to 100 or 1,000, it takes longer and longer. But on the 1,001th clock cycle, there's nothing to say that we're not going to get a failure there. So this is why we use the induction step. So to use formal, to make a full proof, BMC is useful on its own, cover is also useful on its own, but for the full formal proof, we use K-induction. And this is based on a mathematical proof of induction, which uses a base case and an inductive step, and the two things together create the proof. So we have the base case already, that's what you've seen. We start in an initial state. We assume that the first n steps don't violate any assumptions, and then we prove that the first n steps do not violate any assertions. The inductive step starts at some point in the future. So we're looking at moving from a running state to a failed state. So to make sure that things are running as designed, the first n steps of the inductive step are all the assertions are all converted into assumptions. That's a bit of a tricky thing to realize. We'll have an example of that in a minute. And then the last step has to be proven that it doesn't violate any assertions. And if it passes both of these two things, then we get our full proof. And that proves that the design can never pass into a failed state. So that's the kind of the dream goal of formal verification. So another way to look at that is that the base case, starting at n is 0, we've got, by default, our depth of 20. And in the induction step, we're starting at some point in the future. And the crazy thing about the induction step is the solver is basically putting any value it wants into the registers to make it be like some possible state in the future. So with doing the formal stuff, the hard work is in writing the assertions and the assumptions so that the induction step can work. Because, as we'll see in a minute, it can get a bit weird. So before, we were starting on the left with the bounded model check. But now one way to think about the way that induction works is we start on the right. We find a place that could be a failed state, and then the solver has to work backwards and find 20 valid states so that it could show you that your design is going from a running state to a failed state. And if it can find that, then it wins and you lose. You get the trace, you look at the trace, either you've discovered a bug or you've got a problem with your assertions and your assumptions, and you strengthen the proof. So, back to another little exercise. This counter doesn't have any start signal, it just starts counting. It has been initialized. When it gets up to 22, it gets set back to 0, and we've got a single assertion here, that the counter will never equal 500. Will this counter pass the induction step? If we assume no cosmic rays. I'm not asking you to think about will the counter ever count above 22, because I think we can see that if we didn't get any problems with the silicon or the simulation, that would never happen. But will the assertion fail, given K induction? Hands up if you think this is going to pass. Oh. You think it's going to pass? And hands up if you think it's going to fail. Okay, we've got a lot. Yeah, okay. Why do you think it's going to fail, somebody? Yeah. So I've changed the mode from BMC now to mode prove. So in mode prove, it will always run the bounded model check and the inductive step at the same time. So the inductive step doesn't have value unless you also have the base case. Okay. So we have our startup as before, but now the log is a bit more complicated because we've got messages from the induction mixing with the base case. And one thing to note here is that the base case is starting off at step 0, but the induction is working back from step 20. And we get an induction failed and a base case pass. This time, the trace is called something different. If it fails for induction, it's called trace_induct. And just like you said, magically the solver managed to start there, because the solver can choose anything it wants to put in the registers to simulate this running state. It happens to put 480 there, so that on the last step it fails at 500. So what would we need to do to strengthen this assertion? Clifford gave me a good story the other day, is that maybe you're working with some designers. They've already given you an assertion. You're a verification engineer. They've said the counter must never reach 500, otherwise the bomb blows up. You don't want to change this assertion, even though the induction state is not passed, because you want your designers to still know you're respecting their assertion, but you need to strengthen this proof. You need to add another assertion. So what could we add to strengthen this proof? A higher depth. Yeah, okay, that's one way of doing it. What could we set the depth to? All right, let's do it. It's pretty fast, but if this was a CPU, you probably wouldn't want to fix it this way. Yeah, pass. Only if they both pass that we get the pass at the end. If we want to be sane, though, what other assertion could we add here? Yeah, we could do that. But it would be, if we're using an assume, what it's doing, yeah, that would work as well. So we could do assume counter is like this. Yeah, so yeah. We could also do it like this, just like the first one that we saw. And leave the top one in there for the designers to know we're not messing with their assertions. Say that again, sorry? Yeah, yeah. You'd probably want to remove it. I would want to remove it. But the story that Clifford told me would say that maybe it's best to leave it in there. So that after it wraps, we check that it's back to 0. Yeah, we'll have a look at that later. Okay, so for our busy counter, hmm? Okay. With the assume or the assert? And because we failed the induction, we need to use the trace induct trace. So we need to change it to like this. Happy? Okay. So let's have a look at what happens with the double shift register. You said that this passed we predicted that this was going to pass the bounded model check, and it did. So now, what do you predict will happen when we run it with K induction? Will it pass or fail? I'll give you 10 seconds to discuss. We've got some wise words coming from this corner. Nothing forcing it to be synchronized. Let's find out. So we're currently on BMC, so I'll change this to mode prove. Oops, I'm in the wrong directory. Okay, so we have a pass as before on the base case, but this time we have a fail on the inducted case. So what's happened here? We've got a clock, we've got a chip enable line happening right at the end. And then because the outputs of both shift registers is different, O data goes high, the assertion breaks. So why are the shift registers different? Because this is induction, we can't talk about initial values because the solver is in the future somewhere. Yeah, it's allowed to put anything it wants to inside these registers. So this is a very simple example, but it shows you one of the things that you can run into when you're trying to formally verify a real design, is that you'll have some state, and the solver can put anything it wants into that state, and it's maybe not necessarily whatever would be there. So we need to have a way of dealing with this situation. Yeah, so that's one. So we have, in this particular very simple case, that's one thing that we could do. There's a option in the SBY file where you can say opt merge. Yeah, so then it will get pruned because it's redundant. How could we force that they don't diverge? Okay, we could, yeah, so let's try that. One problem with asserting that they're both equal, though, is because, and this is why I've done this, is that the data for the shift register is inside the module. So I don't actually have access to this in this top-level module. But if you want to buy one of our great licenses, then that's one of the things you do get to do. Otherwise, what we could do is we could put an output from our module that exposes the data, and then we could do that assertion. But then we're also changing the logic, and we would rather, as formal verification engineers, not change the logic. So what other way do we have of ensuring that these two things stay in synchronization? What synchronizes them? Yeah, again, that's kind of think about what synchronizes the shift registers. So if we make sure that clock enable goes high regularly, or enough times, then any garbage state that the solver has put into the register will eventually get flushed out. So I could do something, if I make a little counter, always. How many times is it going to get me? There we go. No. Thank you. And then I can, what would I do here? Would I make an assertion or an assumption? We're talking about internal state. We want to control the space, so we're going to use an assumption. Assume the inputs, but assert, yes. So, yes, so the chip enable is an input, so you're right, exactly. Assume clock enable goes high when C counter equals 0, so it happens once every 4 clocks. Something like that. Let's try that. Okay, we've got the base case passing, but the induction is still failing. So let's take a look at that. We can see our clock enable is going high regularly, but the that dang solver has got put the one in a different place so that it still gets into the wrong position at the end. So because the chip enable is only going high once every 4 steps, and we've got a depth of, by default, 20, what would we need to change the depth to fully flush the random stuff inside the shift register? And this time we get a pass. Any questions so far? For bounded model check, you can do that really straightforward with some assertions and some assumptions of correct input, and then you just start it and you test 20 or 30 steps, however many you want. And that's a great way of getting started. But for the induction step, we need to have a lot more to control how the solver is working, what the solve space is. And actually, these slides here are going to help explain this a bit, the typical workflow. So we've got slightly different state transition diagram here, but we've still got the same that we did before. It's not possible from an initial state to pass to a failed state. And if we have a depth of 5, the bounded model check will pass. But with induction, it fails because it just starts in one of these other states where it can get to one of our assertions, and then it will fail. So we strengthen the proof by adding in another assertion. So it breaks this loop, prevents the solver from starting there. But no, it's just been hand drawn. Super simple. But adding that assertion also is also asserting this state is bad. So the solver has another opportunity now to start from somewhere else. And so we have to add another assertion to further strengthen the proof. And now K induction is unsatisfied. It can't find a way of failing the design. So we win, we pass. We have the bounded model check and the proof. So the design is proven to never be able to pass to one of these bad states. So going back to the beginning, I showed you this pipeline. And we have 3 pipeline stages that can make memory operations, 2 that can do a read and 1 that can do a write. And we want to write a property that only allows one of these enable signals to be high at once. So we've got 2 memory read enable signals and 1 memory write. So last exercise of the day, and thank you for all staying awake, is with your partner, have a little chat about this, write down a property that if it passes, verifies that the pipeline will never cause a memory hazard. Okay. No one told me. Okay. Who would like to volunteer a guess for the Marlan pipeline memory hazard properties? Yeah, only one can be high at once. Okay. Anything else? all of these things would work. I'll show you what we actually have. Which is just adding them together and asserting that they're less than 2. You could do it in many ways. But the point of this kind of presentation is to show you that formal verification tools are available for you to try. They're open source, free to download and use. There's a long history of people thinking that formal verification is too hard. And I think you can see that you can do quite a lot with just, in this case, we've just got a couple of assertions here. We're verifying a whole pipeline. You don't have to formally verify everything. You can just formally verify the one part of your design you're most worried about. You can use the formal tools to cover that certain things will happen, and you can use them to prove that things can never happen. So that's the end of the presentation. If you would like to find out about our training courses or give us feedback about this workshop, I'd be really happy. There's a link on the back here. Otherwise, if there's any questions, if I can't handle them, then I'm sure Clifford can. Thank you.